Any questions? Noting the scarcity of people. SMI.
It is flu season.
Pardon?
It is like flu COVID season, so everybody's getting sick now.
It's sort of shocking to think of COVID as a season though.
Yeah, I know.
So today is the 18th. So why don't we say Master Set, Chapter 7. Who are we from today? All right, so I know that when two things collide, they're going to touch each other for the same amount of time. From Newton's third law, I know that the force on A from B is equal to the negative of the force of B on A. Or sorry, try that one again. The force on A from B is equal to the negative of the force on B from A. That's just Newton's third law, shorthand version. They'll touch each other for the same amount of time, so I'll just multiply both sides by that time. So whatever that time they're interacting. And it's a scalar times a vector. And what is, based on Newton's second law, what is force equal? So this is just the mass of A times the acceleration of A times time is equal to the negative mass of B times the acceleration of B times time. And what's acceleration times time? I think it looked like you said speed. You have seen the road that leads to the ballpark. You're not in the ballpark yet.
Not
So-
angular speed, is it?
Pardon?
Not angular speed, is that?
No.
radius?
It is not angular speed. All right, well, let's drop back to the basics here. What's the math definition of acceleration?
Change in velocity or change in time?
So what's acceleration times time? Yes. Multiply both sides by that time, you get change in velocity. So this is just the mass of A times the change in velocity of A. Is equal to the mass of B times the change in velocity of B. Mass is not a vector. There we go.
Would be not be negative.
It would be negative, thank you. All right, so change. When I'm dealing with a change in something, how do I find change?
The final minus the initial.
All right, so this is just the mass of A times VA final minus VA initial. And that's going to be equal to negative B, VB final minus VB initial. I'm just going to distribute. So I get the mass of A, VA final, minus the mass of B, VB final. Sorry. It helps if I actually did math here. Mass of A times VA initial is equal to negative mass of B, VB final, plus mass of B, V initial. So that's just distributing. As I was mentioned before, physicists don't like writing. And MV shows up 4 different times, and so basically they look at that and they go, well, let's come up with a letter. How about P? Let's just select P equal MV. So this becomes PA final minus PA initial is equal to negative PB final plus PB initial. And they look at this and they go, well, yeah, whatever P is, this is just the change in P right here. That's the change in P of A, but that's not really what gets the physicist's heart all aflutter. What we're gonna do is we're gonna get all the initials on one side and all the finals on the other, so I'm gonna add PBF to both sides, and I'm gonna add PAI to both sides. And so I get PB final plus PA final is equal to PB initial plus PA initial. So whatever P is, I know that the total initial is equal to the total final. That's what gets a physicist's heart all aflutter. So I have P initial is equal to P final. Now, it's hard to tell from the way I'm writing this because they're on 2 separate lines and I don't have lines here. Don't have actual physical lines. But this is a capital P and those are lowercase p's. And the difference is the lowercase p is for an individual object and the uppercase P is a total. Now, you can usually pull it from context, but that's like a 99% rule in textbooks. The capital would stand for the total, and the lowercase stands for the individual. But whatever P is, if my total initial and my total final are the same, this is known as a conservation law. P itself has the name of momentum. And so this is just the shorthand summary of what is known as conservation of momentum. So here's the trigger that to know if you're going to be using this or not. One, if I ask, hey, what's the total momentum? It's probably a good idea you're dealing with momentum. But if there is a collision between 2 objects, it is going to be a conservation of momentum problem. All right, so let's exploit this concept here. Questions before we exploit? Now we can actually do this, now that Luis has bothered to show up.
Good morning.
Good morning. You get us? Okay, so I have an object here, A, heading to the right. Let's give the mass of A is 5 kilograms, heading to the right at 2 meters per second. I have a mass of B heading to the left. And so the mass of B, let's make 4 kilograms, and it is going to the left at 3 meters per second. So just start out with a very simple, this is before the collision, so this is before the collision, what is the momentum of A? Give me the whole thing. Alright, so how'd you get 10?
5 times 2.
Yeah, so momentum, mass times velocity. So the momentum, 5 kilograms times 2 meters per second. 10, what would the units be?
Kilogram meters per second.
Yes. They have not bothered to come up with a single word unit for momentum. Why? Yeah. If you really don't want to write kilogram meters per second over and over again, there's a slightly shorter version. If you look over here, I start out, when I do force times time, the units of force times time would be the same units all the way through. I get to force times time is equal to, in essence, the change in momentum of A. So momentum would have the same units as force times time. So you could use Newton seconds. A Newton second is the same as a kilogram meter per second. So this is equal to 10 Newton seconds. Perfectly fine. Now, if you still, that's too much writing for you, you can make up your own unit. However, the ground rules are, 1, do not use a unit that's already being used. If your name is Ned or Nathan, do not use a capital N to represent a Newton second, because capital N has already been used. A unit that we don't really ever deal with in this class, ever really? A unit that I do not deal with in this class, except in this one context, I use a capital D, but it doesn't even have to be it does not even have to be a letter. I've had students come up with certain unique squiggles. But the deal is that if I'm going to use capital D as my unit, I have to define it. Because otherwise, it's wrong. Because this is not a standard preset unit, I have to define D as a kilogram meter per second or a Newton second, either one. The 3 lines there indicate my definition, or I'm defining it to be such. And with that written there, this is also equal to 10 D for Descartes. When Newton was doing his work on forces, Descartes was doing work on what we now call momentum. And I think Descartes is the reason that letter P is used for momentum, and it stands for something. I saw it once, I did not write it down, I thought, oh, I'll remember that, and of course I didn't. But there are a bunch of videos out there of people saying they use P for momentum because nobody knows. But I have actually seen what it stands for. Or maybe that person made it up. Anyway, I use D as in Descartes, so 10 Descartes, 10 Newton seconds, 10 kilogram meters per second, but again, this last one is only valid as long as that's written somewhere. If you write it at the top of a test or quiz or homework or master set, I'm assuming that covers the entire test or assignment. Questions to hear? Then what is the momentum of mass B before the collision?
12 seconds.
12 what?
Newton seconds.
That is not right. I know exactly how you got 12, but there is a mistake there.
Because it's going in the other direction?
Yes, so how would we indicate it? Direction, we do not lose direction in this. Unlike energy, direction matters. And the reason this is negative is because when Ethan said 10 over here, he did not make that negative. So at that point, he established our convention of to the right is positive. Whether he knew it or not, he did establish the convention for the rest of the problem. So this would be P A initial and P B initial. So what? And that's a capital B there. What's my total initial momentum?
2? No,
-2.
Yeah, don't forget the negative. -2, what units do you want to use?
No, it's per second. Oh, these are.
What do you want to use, Ethan?
The D.
D? All right, so -2 Descartes. Next question I'm about to ask is a very simple question and has a very simple answer. However, I've done this on tests and really flummoxed students with it. These two are going to collide. What is the total momentum after the collision?
-2D.
Yes. It's the exact same thing. That's the whole idea. They're going to collide. Momentum is conserved. Especially if I have only two objects. Now, in reality, two cars crash into each other. You have to take into account that, yes, momentum is conserved mostly, but there are more than two objects involved in a car crash because there's air, there's the ground, and there are other complicating factors. One more bit of vocabulary. We have force times time, and you work your way down the left side. That's going to be equal to the change in momentum of A. The change in momentum, or the force times time, has a special name. And I'm going to spare you from the 70s TV commercial reference, but it's called impulse. Typically I ask the question, I suspect it's the most obscure reference that I make. When someone suddenly buys you flowers, that is called impulse. Perfume commercial from the late 70s. I assume that scent's not around anymore. Or at least they don't advertise. Okay. So they're going to collide. There are three basic types of collisions. The perfectly inelastic, the imperfect, and the perfectly elastic. Now, not every textbook is going to use the exact same vocabulary. What I call perfectly elastic, so this is Fox speak, perfectly elastic. Some textbooks will call perfectly elastic. And some textbooks will just call elastic. What I call an imperfect collision. The textbooks that call this one perfectly elastic will call this elastic. And the textbook that call this elastic will call this inelastic. Hopefully you can start to see why the naming convention gets really confusing, and since I work in different textbooks, I really can't keep track which textbook uses which convention. And then what I call perfectly inelastic, the textbooks that use perfectly elastic and elastic call this inelastic. And the ones that use elastic, inelastic will call this perfectly inelastic. And so I just took the ones that were unique, the perfectly elastic, perfectly inelastic, and then a student suggested, and I liked it, imperfect. There's one more category, which I will call Flubberesque. Which both of them will agree is impossible. Flubberesque after The Absent-Minded Professor, the sequel, the remake, then the other remake. the Robin Williams one was called Flubber?
Mm-hmm.
Okay. Actually, mine professor being the original. All right, questions here before I actually talk about what's the difference between these? Then let's talk about what's the difference between these. It all deals with the energy. In a perfectly elastic collision, the change in kinetic energy is zero. So whatever the kinetic energy is here, it will be the exact same afterwards. In a perfectly inelastic, we're going to have the maximum amount that we can lose of kinetic energy, so maximum loss of kinetic energy. And the characteristic of perfectly inelastic is that they stick together. In the imperfect, they don't stick together, but you lose kinetic energy. So no stick, but changing kinetic energy is less than that. So final, you end up with less kinetic than you started with. Flubber-esque, you gain kinetic energy. Now, it is possible for me to have an object and have it gain kinetic energy, so if I had an explosive device, if I had something that just pumped energy into the system. But if I have two things crashing into each other, there's nothing pumping energy into it traditionally. All right, questions before we actually solve this, given one of those conditions? All right, let's start out with a perfectly inelastic collision. Since they stick together in the perfectly inelastic collision, well, I will abbreviate that. PIC, the perfectly inelastic collision, they are going to stick together. I already know what the total momentum is, same as the initial. So my final total momentum is -2 megahertz. And that's going to be equal to mass times velocity. Well, you can think of